So I went with the second one for the first on this week's problem set. I'm in the final. So let's see. So it's asking us to find the Malcolm series for x squared ex. For that, ex plus one plus x squared over two, union x cube over three, fx x squared ex. Let's see. Okay, yeah. So it's x squared times one plus x squared over two, x cube over three, and just again continuing x squared x. Just after further simplifying it, that's the Malcolm series we end up with. So for the second one, it's compute f100 0 the 100 there with 100 with 0. Okay, so pretty straightforward again. F100 at 0 x squared x equals to n to 1 to infinity xn plus 2 over n plus 2 equals to 100, n equals to 98, x to the power 100 over 98, differentiating with respect, differentiating both sides, 199, which is 9,900 for E3x. So from what we know, we can replace x by 3x. So for 3x multipliers, yes, that's what we knew, and the same thing again, but 1 plus 3x plus 9x squared over 2 plus 27 cube over 3, and just yeah, again same. See for problem B for the again just by using this problem B, same thing again. Just take 1 plus 3x plus 9x over 2 plus 27 cube over 3, and just straight up multiplying 3 into 3, 3 3s 9s, 27s, 81s. Yeah. So for ex plus 3, so we know that um ex into e3, e3 1 plus again, just take it on the outside, and after you further expand it, that's the answer you end up with, and it just keeps going. Again, this is e to the power x plus 3. That's e to the power x plus 3. Yeah. So we just add 3 to both sides, 3 on this side. And after adding 3 to both sides, we just end up with the x plus 3, 4 plus x squared over 2, x cubed over 3. And coming to 6. Consider the polar curve R, 1 over cos theta 1 sine theta, 0 to the pi by what happens to R as theta versus pi by 4. So we can simplify the polar curve equation by multiplying both sides by cos to obtain. So it's multiplying cos on both sides, and we can identify um sine theta, sine theta, 2 sine theta cos theta. We know that r cos theta is equals to 1 minus 1 half sine theta. Now as theta approaches pi by 4, sine 2 theta approaches 1, so then the term 1 half sine theta approaches 1 half, therefore we have r cos theta equals to 1 minus 1 half sine 2 theta, which is 1 1 minus 2, which is 1 2. As long as r is positive, we can divide both sides by cos to obtain r 1 half sec theta. So we see that as theta approaches pi by 4, the polar curve r approaches the limit 1 half sec pi by 4, which equals to square root 2 by 2. Therefore, the point r theta approaches the polar point at square root 2 by 2 and pi by 4. Find the slope, no, sorry, calculate the area inside r sine theta 4 theta. So to calculate the area inside one leaf of the rows, we can use formula area for region. That's the formula we know for those. The rows are r equals 3 sine 4 theta. The limits of integration from 0 to pi over 8, which converges one leaf. So we have area using, we know that. From here, just plugging values in using the double angle identity, sine theta 2 theta equals to 1 half minus 1 half cos 4 theta. We can write sine theta, sine 4 theta equals 1 half minus 1 half cos 8 theta. Substituting this integral, we get, that's what we get. This substituting, evaluating from 0 to pi over 8, we get a equals 9 by 8 pi over 8 minus 9 by 32 sine theta. That's the answer we end up with for the area. Find the area under the parametric curve since x equals sin theta, y equals cos sin theta. To find the curve r equals to 2 minus 4 cos theta as a vertical horizontal, we need to find the where dr over d equals to 0. And by taking the derivative of r with respect to theta, we get dr over d theta equals to 4 sin theta. Therefore, dr over d theta equals to 0 and sin theta equals 0. This occurs when theta equals to 0 and pi 2 pi, which corresponds to point 2 0, 2 minus pi, and 2 minus 2 pi on the polar plane. To find where dr d theta is, we need to find where cos equals 0, obviously, since this would make the denominator of the derivative 1 minus 4 cos square theta to the power 1 half equal to 0. This occurs when theta equals pi by 2 and 3 pi by 2, which correspond to the points 0 pi by 2 and 0 3 pi by 2 on the polar plane. Therefore, the curve r equals to 2 minus 4 cos theta has vertical tangent length 2 equals 0, 2 minus pi, and 2 minus 2 pi, and horizontal tangent length at 0, 2 pi over 2, and 0, 3 pi over 2. Region R is bounded by the curves y equals to x squared plus 1 and y equals to 3x minus 1. Set up integral for the volume of solid obtained by rotating R by calculate the volume. Okay, so line at x equals 4 is a vertical line passing through a point 4 0. We'll rotate the region R about this line of plane. So line's probably like straight like this, and it's just cutting through 4 from this corner to the other. Next, we're going to express the curves that bound R in terms of x so that we can use them to find the height and the radius of each cylindrical shell. Solving y equals to x squared plus 1 for x, we get x equals to plus or minus square root of y minus 1. Since we are rotating about x equals 4, we'll shift the curve to right by 4 units. X equals to 4 square root of y minus 1. Solving y equals to 3x minus 1 for x, we get x equals to y plus 1 over 3. Since this curve is already in terms of y, we don't need to shift it. Now we can find the height of each cylindrical shell by subtracting the x coordinate of the lower curve from the x coordinate of the upper curve. Now h equals to 4 plus square root of y minus 1 minus 4 minus square root of y minus 1 equals to 2 square root of y minus 1. And we can find the radius of each cylindrical shell by using the x coordinate of the lower curve. Thus the volume can be expressed by integral v equals to integral 1 comma 10 2 pi 4 minus square root y minus 1 2 square root y minus 1 dy. Simplifying the integral, we get that value, and after further simplifying the volume value, that's the 1173 pi cubic units the value we end up with. Therefore, the volume of solid plane using R about x equals 4 is 1173 cubic units. Again, the volume of course by x y equals 1, y equals 1, and x equals to 2. Set up an integral for the volume of solid obtained by rotating R about the line by minus 1 and calculate the volume. See what I did for this. We set up an integral for the volume of solid plane by region R bounded by curves x by 1, y 1 points, but the line will use with circling shows again. The line y minus 1 is a horizontal line passing through the point 0 minus 1. We'll rotate the region R about this line to obtain x. We need to express the curves that bound R in terms of x, in terms of y, so that we can use them to find the height and radius of each cylindrical shell. Solving xy equals to 1 for x, we get x equals to 1 by 1. Since we're rotating by y minus 1, we'll shift the curve down by 1 unit. X1 y minus 1. Solving y equals 1 for x, we get x equals to 1. Since this curve is already in terms of y, we don't need to shift it. And x equals to 1 already in terms of x, so we need to express in terms of y. 2y equals to 1 over x, y equals to 1 half x. Now we can find the height of each cylindrical shell by subtracting the y coordinate of the lower curve from the y coordinate of the upper curve. Minus upper, and we can find the radius of each cylindrical shell by using the y coordinate of the lower curve. Thus, the volume of solid can be expressed as an integral. Again, simplifying the integral, we get 7 pi over 2 cubic units, and the volume of solid obtained by R about y minus 1 is 7 pi by 2 cubic units. For this one, that's our boundary. Equilateral triangles, right? Yeah, cosine lines are equilateral triangles. We can use the method of slicing to find the volume of solid. Since the cross sections of equilateral triangles perpendicular to the y-axis, we can slice the solid into a series of thin slices perpendicular to the y-axis, each of which has triangular cross section. Let's first sketch out everything complete. The boundary curve of the outer region is given by 16x squared plus 9 by pi by 2. Solving for x, we get so hold up. So the boundary curve is that, and we're solving for x, so that's a value in a bit. Y equals to 4 over 3 square root 9 minus 4x squared. 4x to the power 2, so not squared, same thing. Range of y values that the elliptical region spans from -3 to 3. You then slice solid into a triangle sizes with perpendicular y-axis, where the height of each size dy of the length of each side of the equilateral triangle cross section is equal to the width of the elliptical region at the height. Let's consider the slice at height. Y with thickness dy, the width of the slice at height is 2x. Because it's double. That where x is given by x equals to 3 over 4 square root. We already know the x from up. Already know the x. And thus the area of the triangular cross section is given by 1 half bh. So it's plugging those values in, substituting for x, we get substituting the x value and paste that. It's 3 by 4 multiplies it to 2. And so the volume of size is then given by the d equals dy. We can integrate this equation over the range from y -3 to 3 up to the 1. Again, we're just integrating it, simplifying this integral, we get eventually end up with 3 by 2 square root 3, 8 by 3, and 8 to the 8 square root 3 is keeping that answer for the volume of the solid.